Hello everyone. Today I would like to continue to talk about topic 2, and because I have not received any requests about the tutorial for the homework, so I provide a tutorial of one of the questions I think is kind of challenging, and I think by listening to the tutorial of this question potentially can help you to solve the other questions. So the question basically asks you to present the corresponding high-level explanation of the sequence of the instructions, and the sequence of the instructions are as follows. So I will not provide a one-by-one explanation in detail because this is the homework, but I will provide a sufficient explanation. Hopefully, it will help you to solve the questions. So I want to say is the first and the second instruction together will provide you the calculation of the memory address of certain element of the array. So the first assembly language relate to the operation shift left logic. If you recall, in the previous class we mentioned shift left logic, besides providing the logic operation, also provide the alternative way to calculate multiplication. In other words, if I do shift left logic T0 S02 is equivalent to calculate S0 times 222, and using that the multiplication result to update T0. Just one more time, basically is calculate T0 is equal to S0 times 222. After that, this T0 basically provide the offset, and the second instruction help you to calculate the memory address based on the base address given by 6 and offset given by T0. Similar calculation reflects by the third and the fourth assembly language. After that, I will implement the load word. I think here my comments is writing a wrong line. This comment should be in the previous line. So I highlighted this comment is because I think the hint given by the textbook is not really appropriate. Because here I tried this assembly language try to load certain information or certain data from the memory to the register, and this cannot reflect properly by high-level language, because high-level language only show the relationship or operation on the high-level variable rather than hook back to the physical locations. However, load or store word, this kind of data transfer operation will include the operation on physical location. Therefore, I think rather than write or explain this instruction by using f equal to AF, it's more appropriate to explain that as the S0, which is the physical register, equal to AF. I think by using this explanation as the corresponding explanation for this load word assembly language, you suppose can get a better idea of the coming different instructions. So basically, I load a certain data and from the memory based on whatever memory address I solved by the previous 4 instructions. After that, I will do certain operation, which is addition on those information load from the memory and store currently in the register. After that, I will restore the arithmetic operation results back into the memory address, which is indicated by T1 plus 0, which is T1. And by doing so, actually what I try to do is I will replace the high-level variable whose value currently stored in this memory address T1 with the results which currently is stored in T0. Okay, just overall, the first of 4 assembly language calculate the memory address of 2 different elements of 2 different array, and then I will load the individual data from the memory into the register and do certain arithmetic operation on those registers. After that, I will using that results to replace the value of the high-level variable which currently stored in the memory address T1. I hope that the question is give you some idea solving the other question, which is very similar to this one. And the left question, this homework, I think is easy. Basically, give you the machine language, or we call the instruction, and ask you to tell what the representation of those instruction is, basically binary sequence of binary numbers, and what kind of format it is. So if you understand like R format, I format, what how many segments they contain, what exactly the characteristics of the individual segment, you're supposed to be able to solve that problem. Okay, so now we continue to talk about the material of the section 2.7. Again, this index represents the index you can find the corresponding material in your textbook. In last class, we talked a lot about the branch if equal, branch if not equal. We talked about how to translate corresponding high-level representation into the assembly language containing this control transfer operation, branch equal, branch not equal. Here we continue to talk how to represent corresponding assembly language containing branch equal, branch not equal into the machine language, or we call the instructions. As we mentioned in last class, although in the branch if equal, branch not equal, we have the label which is ASCII character, for example L1. However, when we represent those assembly language into the machine language, those sequence of binary number will not allow to contain any ASCII characters. Instead, they will translate those ASCII characters into the corresponding memory address of the instructions having this ASCII character as the label. See one more time, basically we'll translate this L1 in this example into the memory address of the instructions having L1 as the label. Because of that, the instruction format should be I format instead of R format, because in I format we have one segment which called immediate field, can use to contain the binary numbers, which totally is a 16-bit. And as we mentioned in last class, the memory address of any instruction suppose has 32-bit. However, here this segment only has 16-bit. Therefore, we need to use this segment smartly and effectively enough to represent as large range as possible for the memory address of the certain targeted instructions. In order to do so, we borrow the idea of representing the memory address of the data in the memory when we represent load word, store word. If you recall, the memory address of the data we want to load from or store into is not directly represented in the load or store word. Instead, we will represent that memory address as the offset, just right here, offset plus the base address, right? So in other words, we can represent, for example, if offset is 4 and the base address is contained in the register as 0, we can represent the real memory address as the following. Similar idea, in here we can also represent the memory address of the targeted instruction by using the reference address PC plus 4 and the relative memory address. Say one more time, basically in branch of equal or branch if not equal, instead of using that segment, 16-bit segment to represent memory address, we try to leverage that segment by representing the memory address as the summation of the offset, which reflected by the immediate field, and the reference address, which is equal to program counter's value plus 4. I just want to emphasize one more time, program counter contains the memory address of the currently running instructions, and the PC plus 4 represent the memory address of the next instruction by default, which will be the memory address of the instruction right after the currently running instructions. And we also mentioned, basically until now, you should know in this segment, should contain the relative address between the instruction with label L1 and the instructions memory address, which is PC plus 4. And as we mentioned in last class, because here all the instruction will be 32-bit bytes, therefore all the memory address of all the instructions will be multiple of 4. And if the decimal value can be represented by multiple of 4, in the binary representation will be represented as all the memory address will have 2 zeros at the end. Because of that, I don't want to waste 2 of the 16-bit, which is last 2 of the 16-bit, to represent 2 zeros, although I know there will be 2 zeros in advance. Instead, I will using this 16-bit to represent the relative memory address, which is right before these 2 zeros. Instead, or in other words, what I represent here is using the 16-bit binary number contained in that segment and do 2 zero extension at the end. The overall will represent the relative address between the instruction with certain label and the reference address PC plus 4. In other words, I'm using this 16-bit segment to represent a 18-bit binary numbers, which is the reference address, relative address. And I think in this high-level hardware implementation can present a better idea. So basically, I will take that 16-bit in this immediate field, and then which is represented here in this orange color, and I do 2 zeros extension, and now the overall 16 plus 2 is 18-bit binary numbers will represent the relative memory address. And I will using the information reflected by this 18-bit binary numbers with the category summation with the PC plus 4, which is represented in this segment. You can see there's this adder. One of the input of the adder is PC, another input of adder is 4. These two add together, the output of this adder will be PC plus 4. But here Will has a question. Because PC is a 32-bit binary number, 4, although it's constant, still represented as a 32-bit binary number, so the output of the adder is still 32 binary number. I cannot, using this 32 binary number, directly add with the 18-bit binary number, which is represented as the relative memory address. Therefore, I have to translate this 18-bit binary number into a 32-bit binary number and then do the summation. If you recall, when we learned the binary numbers, we mentioned if this binary number is assigned binary number, I can just extend the number of bits by do the sign extension. That is exactly what we try to do here. Basically, I will take the sign bit and then repeat another 14 times in order to achieve equivalent value binary number, but this equivalent values binary number has a 32-bit now. And then I will using this 32-bit with the PC plus 4, which is 32-bit 2, and add them together. The output of this adder will get the memory address of the target instructions with the certain given label. And if I using the let me just look at, if I try to use the mathematical equation to represent, basically the output of the last adder will be the memory address of the target instruction with certain label. That memory address will be equal to PC plus 4 plus 4 times x tilde. This x tilde is the information contained by that 16-bit immediate field for the instruction of branch if equal, branch not equal. So this, if this is the instructions of branch if equal, branch not equal, and then this last field, if the overall equivalent value is execute, the real memory address of the targeted instruction will be PC plus 4 times execute. If I want you to try to think by yourself why here's 4 times, why here's PC plus 4, and if you still have questions, please let me know. And that mathematical equation exactly equivalent to the operation represented here, and we just say PC plus 4 times execute exactly is output of this adder. Okay.